Hello there and welcome to my video on arc length in polar curves. This is a part of my lecture video series. So let's get started. The arc length of a curve defined by a polar function is given by this formula from the textbook. So the length is equal to the integral from alpha to beta of the square root of the function in terms of theta squared plus the derivative of the function in terms of theta squared d theta. So in this first example, we have a cardioid. And we know that this is a cardioid because the 2 and the 2 are both the same number. And so we're going to get a graph that looks something like that. If you don't believe me, we can go into Desmos. And we will put Desmos, put the function in here. R is equal to 2 plus 2 cosine of theta. All right, and so we are looking to integrate where alpha is 0 and beta is 2 pi. So one complete rotation around, you might say. And so the bounds are given right here, because that would give us the entire area enclosed. So, plugging into the formula of the integral from 0 to 2 pi, and then we have the square root. We want the function squared plus the derivative of the function squared. And so the derivative, r prime, the derivative of 2 is 0. And then the derivative of 2 cosine, well, the derivative of cosine is negative sine, so this simply becomes negative 2 sine of theta. And so that is in right here. Now comes a little bit of algebra. We need to expand both of these. And so we take 2 plus 2 cosine theta is going to be 4 plus 8 cosine theta plus 4 cosine squared theta. Negative 2 sine of theta is 4 sine squared theta. So now we have to do some more tricky algebra / trigonometry work to try to simplify this. And so we notice that we have a sine squared, cosine squared with the same coefficient here. So essentially I'm factoring a 4 out, leaving us with sine squared theta plus cosine squared theta, which we know is equal to 1. We have the Pythagorean identity that sine squared theta plus cosine squared theta is equal to 1. So we substitute 1 in there. 1 times 4 is 4, plus this 4 gives us 8 plus 8 cosine theta. Now here's the tricky part with this one. First of all, you can simplify that. You can factor out the 8. Well, you can factor actually out a 4 and the square root of, so what we're doing here is we've got the square root taking out a 4, leaving me with 2 plus 2 cosine theta. And then the square root of that 4 becomes 2. And so that's where this 2 comes from out here. Now, what do we do with this? We don't know how to integrate that. That's not something that is integratable by any technique we know. Now, of course, we could use tables perhaps, or we could use numerical integration. But in this particular case, we can do a little bit more algebra and trigonometry magic. And so that is over here. We have to go to this particular trig identity. Now, I never expect you to memorize all of the trig identities or formulas or anything like that unless I use it in class. If a trig identity, if any type of a formula or equation is used in class, it's fair game. So now that this one is being used, I would strongly suggest that you remember it. So we have cosine of 2 theta is equal to 2 cosine squared theta. Take the 1, add it over to the other side. So this 1 is just coming over to the other side. So we have 2 cosine squared theta is equal to the cosine of 2 theta plus 1. Now we're simply multiplying both sides of the equation by 2. And we end up with this. So we're beginning to look a little bit like what we have under here, except this is still a 2 in here. And this is not. This is just a 1. All right. And so then multiplying on the right-hand side by 2, we end up with 4 cosine squared theta. Well, if we, in this trig identity, we have an identity that we started off with 2 times the angle, but over on the other side, it's simply just the angle. It's half of what this is. So if I change this from 2 down to 1, then this is going to go from a 1 to a 1/2, which is what this is. Theta divided by 2 is 1/2 theta. And so now this is what we have under the radical. And so I'm going to substitute in 4 cosine squared of 1/2 theta, which we have right here. Now, why do we want to do that? Well, we've got ourselves a perfect square underneath the radical. Square root of 4 is 2. And so that 2 gets multiplied by this 2 to give us the 4. And we have cosine of 1/2 theta squared. And so the square root of that is the cosine of 1/2 theta. All right, and so one last little trick here to make it a little bit easier is using symmetry. If we go back and look at our graph, we're starting with from 0 to pi. We're finding the area from 0 to pi all the way up to here. And then from pi all the way up to here, we're finding the other half. So there's symmetry here because this is symmetric about the x-axis. If we simply find the area from 0 to pi, it's going to make it a little bit easier. And so we're going to change the bounds of integration from 0 to pi rather than 2 pi, but then we have to multiply the 4 by 2 to get 8. So we have the cosine of 1/2 theta. Now we can also remove the absolute value because the values of cosine between 0 and pi are going to be positive when we take that angle and divide it by 2. Because what we're really going through, the largest angle that we're going to have here is pi divided by 2. And so if we just look from 0 to pi over 2, we're in the first quadrant. From 0 to pi over 2, all of our angles are positive cosine angles. So we don't need the absolute value sign anymore. All right, so finally we can get to something that we can integrate. And so the integral of cosine is sine of 1/2 theta divided by 1/2 or times the 2. So it's, well, we get the 2 out here. 2 times 8 is 16. So the length, the arc length is 16 times the sine of theta divided by 2. And we are evaluating that from pi to 0. And so we have 16 times the sine of pi divided by 2 minus the sine of 0 divided by 2, which is 0. And so the sine of pi over 2 is 1, and the sine of 0 is 0. So we have 16 times 1 minus 0, which is 16. And that would be the arc length. So the reason that I'm putting this into my lecture notes and going over it in the video is because there's all kinds of algebra and trigonometry in this problem. Lots and lots of good algebra and lots of good trigonometry stuff that we need to know to be able to go through and do some of these problems. So I hope this was helpful and see you in the next video.